first of all, let me introduce you to our audience. So, dear colleagues, today we have a seminar with Dr. Iñigo Liberal. So, some points from his biography. So, he finished his PhD back in 2013 in the University of Navarre in Spain. And then he did his postdoc in the group of Navarre and Guetta in the University of Pennsylvania until 2017. And currently, he is a fellow researcher again at the University of Navarre, so back in Spain. He got famous in the context of research on near-zero, epsilon near-zero metamaterials. For instance, a review paper in Nature Photonics on near-zero refractive index photonics. And so today he will tell us some recent results in this area, both related to classical and quantum electrodynamics. So, Iñigo, please, you're welcome.
Yay, let me share the screen and let us start. Well, thank you. I would like to thank the Maxim and all the organizers for inviting me to the seminar. And actually to say that I am very impressed on how these seminars are being organized. I didn't know them before, but I have been checking a few of them. And I believe you're doing a great job. I think it's a sign that you have a very lively department. And I also believe it has a very positive impact on the field. So I truly hope that this talk also contributes to the success of the seminars. Yeah, please have this talk in the spirit of a seminar, as if we were in St. Petersburg. So feel free to interrupt at any time and to make questions. Otherwise, I will be speaking for 1 hour long and it will be very tough for me. So I'm sure the moderators will be able to handle the questions. So if you have questions, feel free to interrupt. I will definitely up to answering them. Okay, so as Maxim was anticipating, today I would like to share a few aspects of classical and quantum electrodynamics in near-zero index media. And I would like to share with you a few examples of intriguing theoretical concepts that we have been pushing forward during the last years, as well as some recent experiments that we are carrying out in a new research land that we are launching at my group. Okay, let's go. So as a very first introduction to the topic, I believe the idea behind near-zero index media is actually very simple. So the gist of it is that when the refractive index goes to 0, the wavelength gets effectively stretched within the medium, and thus gives access to a regime of qualitatively different electrodynamics. So you basically have different rules for electrodynamics. This was best described, I believe, by the now seminal paper by Professor Tsiolkovsky in 2004, where he rigorously derived that when the material parameters goes to 0, you have pathological solutions to Maxwell's equation, where you have field distributions which are spatially static, but at the same time they dynamically oscillate in time. So again, new rules for electrodynamics. And due to these pathological solutions, you have access to a variety of wave phenomena that have no counterpart in other electrodynamical systems. And this is an idea that has been pushed forward by the group of Professor Ngueta, discovering really very exotic wave phenomena related to these structures and materials. So I got involved in the field like 5 years ago, and mostly I have been doing research with the idea that in these new rules for electrodynamics, even a concept as basic as geometry can play a qualitatively different role. So the idea would be that you may even have observables which are independent of the geometry of the system. And when I say independent of the geometry of the system, it could be even changes in the topology of the system. So for example, something that I won't be covering today is that you can even have geometry invariant resonant cavities where the frequency of resonance of the cavity is independent of the geometry of the external boundary, which is entirely different to any other optical cavity. So it's, again, a new regime for electrodynamics. What I would like to share today is 5 examples of how different wave phenomena may appear when you have near-zero index media. And if I don't have time, please let me know. I run out of time. It's okay. Yes, I will prefer to explain good the examples when I have the time. Okay, so the first example I would like to share is electromagnetic ideal fluids. The idea that the power flow in 2-dimensional near-zero index media is actually equivalent to that of ideal fluids in fluid dynamics. So in a way, you can have ideal fluids of light. The second one is the idea that you can transgress the rules of effective medium theories in a concept that we call photonic doping. So you can homogenize systems for geometries that the usual rules of effective medium theories will not allow you to carry out a homogenization procedure. Okay, I also would like to discuss a little bit about quantum light emission in inertia index media, and this idea that when the refractive index goes to 0, what you are doing is basically depleting the space of optical modes. So in a way, if you want, you can say you are emptying the quantum vacuum. However, there is a complex limiting procedure, and you can have non-trivial quantum light emission even in a space depleted of optical modes. At the same time, you have to be very careful because inertia index media usually takes place at the edge of a propagating band. So you have to be ready to take into account the non-perturbative aspects of decay dynamics in order to get an accurate prediction of the response of quantum emitters in inertia index media. And finally, I would like to share with you, as I was saying, the very first experiment we have carried out in my lab. We are trying to develop a technology of thermal emitters based on these exotic properties of epsilon near zero media. Okay, so let's start. The first idea, this idea that you can have electromagnetic ideal fluids. And I think the best way to introduce this concept is to come back to the old effect of supercoupling, which is the fact that you can have perfect transmission with zero phase advance through a deformed waveguide, quite independently of the geometry of the deformation of the waveguide, which is an effect that was discovered by Mario Silverini and Professor Engheta and has now been experimentally verified in quite a few platforms, and it has been proposed for many applications. However, when looking at this effect, we were thinking that it has been studied in detail, that it takes place and the potential applications, but in our humble opinion, it has not so been explained so well why and how it locally takes place. In other words, it has been studied a lot that the power indeed goes from one end to the waveguide to the other end of the waveguide, but how does this process take place locally has not been studied so in detail. And in fact, it is interesting how it happens, because when you look at the usual power flow distributions that you can find in the literature, you can see that the power flow in the supercoupling effect is very smooth. So basically you have no optical vortices, you have no point where the power flow is flowing backwards, you simply have the power flow moving forward and adapting to the geometry of the deformation. So it's it looks like it is a very particular power flow distribution. And in fact, if you compare it with other resonant transmission effects, like for example, you could finely tune the permittivity of the material filling the waveguide so that you indeed get also a perfect transmission. That can happen, but when you look at the power flow distribution, you see that it is more noisy, and you have the formation of vortices, and you have power flow moving backwards, and so on and so forth. So in view of these sort of simulations that you can find, yeah, sorry, Maxim.
So Iñigo, I see a question from the audience, Sasha Poddubny.
Yeah, I'm sorry, very naive question regarding so I understand a little bit about the supercoupling effect. What I want to ask is the interface between normal material and epsilon near zero material important? So does it have to be an abrupt interface, like epsilon is something then zero, or does it have to be a smooth interface between epsilon non-zero and zero?
Okay, so by a smooth, you mean like the material will change slowly or something like that?
Yeah, in order for this to work, does the permittivity have to decrease from, say, 10 to 0 smoothly and then go backward smoothly back to 10, or you can make it a very abrupt transition, 10, 0, 10?
Yeah, actually, so it has always been derived for entirely abrupt transition. So what happens basically in a theoretical model, what we have is like this interface where you go from 1 to 0 in no time. So it works even for abrupt transition. Maybe what I think, maybe I may think that your question is anticipated by the fact that if you only have like a permittivity, if the medium is not much, you should expect a very high reflection at that interface. That's something that usually confuses people. So the trick here is that you have a finite size system. And then the mismatch in permittivity does not give you a good account of the reflectivity when you have a finite size system, right? That equation will only work for an infinite half space. And in fact, in this case, the wavelength is so large that you could always believe that the input and output ports, electrically, they are very close. So the mismatch of the impedance is not that critical in terms of finding the transmission through this finite system. That's how it works.
Thank you.
No problem. Yeah, so please hit me with more questions. I really enjoy when the talks have a lot of...
May I ask one?
Sure.
Mikhail, is it critical that you have PEC walls, perfectly conducting walls?
It is critical that you have a well-defined sort of like propagating mode, waveguide mode, right? That's what is critical. It is not critical that it has to be easy. Like, for example, we have made designs based on photonic crystal, and then we use like a photonic crystal with a band gap outside, and that design may also work in some cases. But you basically need a sort of like an opaque system that allows you for the mode that the waveguide mode that you want. Okay, so I will continue. So the idea is that the power flow has this very smooth and soft distribution. So we decided to investigate it in detail. And then what you have to do is simply to look at the equations of motion of the power flow. So basically the divergence and the curl of the Poynting vector field. Okay. The divergence, there isn't that much special about it. So basically, if you have lossless media, there is no divergence, meaning that there is no sink of powers within the material. And the curl is more involved, and there are more interesting things to study here. But we can simplify it a lot. For example, if you have homogeneous media, the terms with the divergence will go to 0. And if we consider a given polarization and a dimensionality of the system being equivalent to a two-dimensional system, the other term goes to 0. So we only get this very last term contributing to the curl of the Poynting vector field. And there it happens that only for epsilon near 0 media, because in a two-dimensional system, for this polarization, the magnetic field must become constant in order to avoid a divergence of the electric field. We have that it also has to be 0. So in a way, very simple, what happens is that the equations of motion for the power flow reduced to the condition that it has to be divergenceless and irrotational property. And indeed, if you look at the basic textbooks of fluid mechanics, these are the same equations of motions that you find for an ideal fluid. So in a way, as far as power flow is concerned, two-dimensional near-zero index media is fully equivalent to ideal fluid flow. And we will see some interesting things and fun things you can do with this property. But first, let me review a little bit about ideal fluids. So basically, because you have these two properties, you can describe the Poynting vector field as the result of scalar fields, like the velocity potential and the stream function. And again, because of these properties, these two scalar fields are actually harmonic functions, so solution to Laplace's equation. And this is super convenient because there is a lot of mathematical work on harmonic functions, and you can use techniques like conformal mapping in order to find solutions for even complex geometries. Okay, so with this theory, we can have a fresh look at supercoupling and analyze and revisit supercoupling as ideal fluid flow. So for example, we can model a deformation of the waveguide as this elliptical obstacle, which can be solved in fluid dynamics. And we have these distributions for the stream function and velocity potential, right? Basically, there is no turbulence around the obstacle as we were expecting. So what we were claiming is that the distribution will be the same in the electromagnetic system. And this is something you can double check, for example, with a console simulation. And this is what you get for the streamlines of the power flow and the electric field, and they match those of the fluid dynamics theory solution. So again, you can understand supercoupling as ideal fluid flow. But you can do more interesting things and try to make connections between fluid dynamics and near-zero index electrodynamics. And one interesting aspect maybe is to find a connections with airfoil theory. So you can analyze a shape like similar to the wing of an airplane, right? And this is something that also has a closed form solutions, because obviously the wings of the airplanes is something that is of interest for many people. And you can find, again, the stream function and the velocity potential. It looks like it behaves as you would expect from an ideal fluid. Basically, the power flow smoothly around the object, and you have two stagnation points at the front and at the tail of the airfoil. And again, this should be exactly the same solution that you find in the electromagnetic system. And if you double check it with numerical simulations, is what you get. So I don't know, this is an interesting effect that you can find connections with airfoil theory. It may have potential applications in optical forces. It's something we are studying now. We don't know yet for sure. Okay, so when we are talking about near zero index media, this effect or any other effect, it is always very important to point out that it is an effect that takes place in a finite bandwidth. So on the one hand, it's not something that only happens at the very singular frequency point, but at the same time, it's only that is an effect that only survives for a given finite bandwidth. And the bandwidth usually depends on the dispersion properties of your material parameters, as well as the size of the system. It's like you have to fight against the usual physics, and the larger your system, the smaller your bandwidth. So for example, for the obstacle before, you can see that there is a finite bandwidth where the power flow and the streamlines look as an ideal fluid, but then as you move away from that bandwidth, you suddenly have the optical vortices that you should expect for an obstacle. Okay, and to finalize...
Sorry, may I ask you, so your vortices are always on the left from the obstacle? It's because, so why they are on the left and not on the right?
Yeah, actually, I'm not very sure about it. Maybe it's because of the waveguide configuration, because in open systems, I have seen vortices on the shadow and so on and so forth. But I wouldn't know why there is that asymmetry there. Yeah. Thank you. Okay, so another aspect is what is the role of the permeability? Because in my derivation, I found that you only need a near zero permittivity in order to get this response of an ideal fluid. But we know that the value of the permeability has a very important impact on the supercoupling effect. So for example, if you have both permittivity and permeability going to zero, you can have supercoupling independently of the geometry of the deformation. If you have only the permittivity going to zero, supercoupling only takes place in the limit that the area of the waveguide goes to zero, like for any geometry, but in the limiting case that the area goes to zero. So you have to have like a very narrow waveguide. So how to reconcile these two ideas, that the power flow is independent of the permeability, but at the same time, you have a very different macroscopic response, right? And the answer is that the power flow distribution is exactly the same up to a scalar factor. And that scalar factor dictates that the transmission that you get from the system. And that's how you observe macroscopically very different transmission properties. However, if you normalize the plot of the power flow distribution, you find that they look exactly the same and exactly the same to the solution to an ideal fluid. Okay, so again, there is, to finalize this section, the idea is that we have found this supercoupling effect was known for a very long time. We have identified that in two-dimensional near zero index media, power flow behaves as that of an ideal fluid. It has interesting connections with airfoil theory and other areas of fluid dynamics. We are trying to look if it may have any practical implication, maybe optical forces, maybe since optical turbulence is intrinsically inhibited, it maybe make instrumentation more robust against mechanical vibrations. Is something we are looking into it now. But at the very least, it's an interesting theoretical connections between two fields. Okay, so
sorry, I promise this will be my last question. Sorry for too many questions, but your image looks very beautiful. Could you please show it again? This color maps of. So basically, you have blue on the left and red on the right. Yes, for your power flow. In terms of color, it's blue on the left, red on the right. So I wonder, on the left, it's blue because the wave enters from left, or because just the waveguide is broader.
So I don't see actually blue on the left.
Well, I mean the colors in your distribution it's colored by something, and it's red is on the right part.
Yeah. So the color is the magnitude of the Poynting vector field, and it looks red on the right, actually, because now I see it does look red on the right. You were right. It's only because the waveguide is narrower, so you are
Okay. So it's not because it's entering from the left, it's just because it's okay. Thank you.
Yeah. So so it looks green outside the ENC region because it's 1, and then whenever you concentrate more the power flow, then it gets a more redder color. Okay, so the second idea I wanted to talk about is this idea that you can actually transgress the rules of effective medium theories. So basically, I believe most people know here for sure know effective medium theories, but the very basics for the students at least. The idea is that you have a complex heterogeneous system with a lot of degrees of freedom, and this is too complicated for us. So you want to describe it with a very simple system where you homogenize it, and you can describe it with maybe 2 degrees of freedom, like effective permittivity and effective permeability. And this is wonderful to do, but it's such a crude approximation that you can only do it with a lot of restrictions. So for example, you need to have particles which are much smaller than the wavelength of operation. You need to have separation between the particles, which are also much smaller than the wavelength of operation. You have to have a very large number of particles. You have troubles whenever you have a complex boundary with a complex geometry, and you have trouble whenever you interact with near fields. So effective medium theories are a great tool, but they have to be very carefully handled and only applied to suitable problems. Okay, so what we found is that, again, in 2-dimensional systems.
Sorry, may I ask a question?
Sure.
You're right. You compare lattice constant with wavelength lambda. No. What is lambda? Is vacuum lambda, or is lambda inside effective media and epsilon near zero regime or mu near zero regime? It should be very large.
Yeah, so that's part of the discussion. So here lambda will be free space lambda, right? And as you are pointing out, one intuitive reason of why we would be able to violate some of these rules is because in ENC we have very large lambda. Yeah,
sure.
Yeah, so here I was referring to.
And you will show us such results. Okay, good.
Yeah.
Thank you.
Yeah, very, very good intuition. Yeah, so the idea is here's free space wavelength, right? So when you go to 2-dimensional media, you can actually violate some of these restrictions, and you can homogenize the system even if you have a particle of arbitrary size, could be sub-wavelength, comparable to the wavelength, or even larger than the wavelength. You can have separations between the particles that could be also in any length scale. You could have an arbitrary number of particles, so maybe you can homogenize the system even if you have a single inclusion, like a single unit set metamaterial, and for any arbitrary boundary and for arbitrary sources. So what happens is, like, when you have a 2-dimensional near index media and you put dielectric particles, the permittivity continues being near 0. But then what you do is you modify the effective permeability. You modify it in a very interesting way. Like the contributions are additive from the particles, which may seem intuitive, but it's actually very counterintuitive, because having additive contributions is equivalent to say that there is no interaction between the particles, and then they will be independent of the position of the particles. So in a way, this resembles doping of semiconductors, because what you're doing is you are placing an impurity somewhere in your material, and independently of the position, you change the macroscopic properties of the system. In this case, the permeability, independently of where your impurity is located, and the contribution is additive. So we call it photonic doping. Okay, so how is this possible? How is this possible that we can violate all the rules of effective medium theories? So it is connected to the fact that the wavelength within ENC media is stretched, but it's actually more than that. You have more conditions to do so. So the way we derive that it would be the case is by actually solving the scattering problem. So we solved the scattering problem, and we demonstrated that the external fields will be equivalent to those of a body with that effective permeability. So basically, for this polarization, you have to solve Helmholtz equation. And So long story short, the key point is again that in two-dimensional ENC media, the magnetic field has to become constant, and that imposes a lot of restrictions on the field distributions outside the ENC medium and within the dielectric particles. So basically you have like these closed form solutions locked because the magnetic field in the ENC medium becomes constant, and you only have to find the value of this constant magnetic field, which you can do by imposing Faraday's law on the boundary of the object. When you do so, you get something like this, which again, I will omit all the details, but the important part is that you have terms that only depend on the geometry of the external surface. You have a term that depends on the area of the ENC host, and you have a term that depends on the internal properties of the particle. So crucially, the position of the particles is not where it doesn't appear anywhere here, and the contributions from the particles are additive. And more importantly, when you look at this equation, you can compress all the impacts of the dielectric particles into an effective permeability. So that demonstrates that for an external observer, there will be no difference between the fields generated by this body and the fields generated by an equivalent body with an effective permeability. And this is for any illumination that you will want to use and for any geometry and independently of the position of the particles, and so on and so forth. Okay, so as an example, as an American example, we can go to this single unit cell metamaterial and see that we can have effective medium theories even when you only have like a single unit cell. And we go for the toughest case where you have a very arbitrary boundary and you have a near field source illuminating the system. And then applying our equation, we expect permittivity like that when the particle is resonant has a Lorentzian form, right? And then if we operate, for example, near the PMC point, we get these field distributions by using a numerical simulation. And you can see that they are exactly the same. So an external observer cannot tell the difference, despite the fact that the fields, it is very intriguing, despite the fact that the fields are completely different within the body, the external fields are exactly the same. And this description, I believe, is more powerful than the usual field averaging. It is an equivalent scattering solution. So the near field look exactly the same. Of course, if you compute the far field, they perfectly match, but even the near field are very similar. And we can go to other examples. For example, you can operate near the epsilon and mu near 0 point. The fact that the field distribution is complicated, but still you can see that it is fully equivalent in all cases. So it is a very intriguing effect. And the idea is that you can homogenize systems that cannot be homogenized with the usual rules of effective medium theories. And in terms of application, the idea is that you can control macroscopic parameters with a single actuator or with a single device. Okay, so we did a first experiment on this, like the student Ahmed Mahmoud actually did the work on this. We did an experiment by checking epsilon mu near 0 tunneling enabled by this photonic doping. The idea, we use structural dispersion in waveguides in order to have an ENC response, and then we use dielectric cylinders in order to change the permeability following the previously described theory. And to demonstrate the geometrical flexibility of this effect, so we fabricated 3 different cavities with quite arbitrary shapes, and then for each cavity we place a dielectric rod in 3 different positions. So this is 9 experiments in total. And the idea is that if we are able to hit the epsilon mu near 0 point, we have perfect transmission independently of the geometry and independently of the position of the rods. And these are the results of the experiments. There is some losses because of the system, but you can see that you have resonant transmission independently of the geometry, independently of the position of the rod, and with 0 phase advance. So Ahmed was able to experimentally demonstrate in this setup the photonic doping theory. After this experiment, there has been a few more experiments. So for example, Professor Yuli from Tsinghua University have demonstrated this effect in substrate integrated waveguides, not only demonstrated supercoupling, but also demonstrated that he was able to do a generalized impedance matching due to the tunability of the rods. And he has also been designing compact antennas based on this concept. And there have been other experiments based on implementations on photonic crystal implementations, which are interesting. they do suffer from a spatial dispersion, so there are some geometrical restrictions there, but at the same time, they are basically all dielectric platform, so they may be suitable for integration at near infrared frequencies. And it has been experimentally verified, and it could be an option for integrated photonics experimental demonstration of this concept. Okay, so we expanded this idea to the nonlinear system too, and what would happen if you have a nonlinear dielectric doping your ENC medium. I am not going to spend a lot of time here, but basically the idea is that you are able to get an effective permeability and in a way a non-perturbative effective permeability. This works similar to a nonlinear system enhanced with a resonance, but it has two main differences. The two main differences is that nonlinear system can be described through effective parameters, again, so you get a magnetic nonlinearity, which is interesting, and you're able to operate near the resonance of the permittivity. And by doing so, you are able to tune the transmission coefficient, for example, which will become intensity dependent. But more interestingly, another difference is that this nonlinear effect, again, is described through effective medium materials. So you are able to maintain a description even in the near field, are fully equivalent. So again, it's resonantly enhancing nonlinear effects, while at the same time having this effective medium response description even in complex boundaries. Okay, so
I wonder regarding your analogy with liquid, nonlinearity is more like turbulence or more like viscosity, or what does it add to this picture of your ideal liquid?
Yeah, so that's a very good point. When we have nonlinearity in the ENC medium, it would definitely introduce some viscosity. That's actually a very interesting suggestion. How would you move away from that? But here, the nonlinear part is only within the dielectric dopant. So in that sense, there will not be no viscosity in the electromagnetic fluid description of the system. It's more like you will have like a viscous system within ideal fluid conduit or something like that. Yeah, but that's an interesting observation. It will be worth studying, like when you add a little bit of nonlinearity, what happens to the ideal fluid flow and how it becomes viscous and Reynolds numbers and so on and so forth. Yeah, very nice suggestion.
Iñigo, and another question. So you mentioned that you insert some inclusions with electric nonlinearity, but then the whole structure exhibits magnetic nonlinearity. Can you comment, please, on the mechanism, how this happens?
Yeah, exactly. So that's one of the main difference with other nonlinear systems. So the idea is that this photonic doping, what happens is you put a dielectric, and then as a function of the internal properties of the particle, like geometry and permittivity, you get an effective permeability for the entire system. So then when you change the values of those permittivity, like for example with Kerr nonlinearity, then you get a change in the effective permeability. So that's how an electric nonlinearity becomes a magnetic nonlinearity.
Thanks.
Okay, so that was for photonic doping. Again, the idea that you can violate some of the rules of effective medium theories in inertia index media. Okay, now I would like to talk a little bit about quantum light emission in inertia index media. And this is a topic I really enjoyed. The idea is the following. If you think on the usual quantization volume, which is a dangerous thing to do, but if you do it, if you think in terms of the quantization based on a cavity, it is very clear that whenever you have the refractive index going to 0, you're going to have a depletion of the density of optical modes, the spatial density of optical modes, right? And that will intuitively tell you that you're going to be inhibiting all quantum transitions within inertia index media. And that's an intuition that is partially true, but it's not always true. So it's worth discussing even in the simplest cases. The idea is that when you go to the inertia index limit, you have a complex limiting behavior, and any response may be possible. So let's discuss it a little bit. To approach this problem, we use the usual simplest Hamiltonian, where we have a two-level system coupled to a bath of photonic modes using the usual rotating wave approximation, nothing really special. but we follow Miloni's quantization approach, right? And there, the only difference is that the coupling strength critically depends on both the dispersion properties of the material properties themselves through the intrinsic impedance, and the dimensionality of the system. So then, for example, if we compute the spontaneous emission decay rate, we get the usual expression, like no difference with with any other system where you couple a two-level system to a photonic mode. However, there is something that is, I believe, usually missed here. So let me explain it very, very carefully. You need modes, you need optical modes to couple to them in order to have a spontaneous emission. And that's clear from the summation that appears on the right of the spontaneous emission decay rate. But as critical as the density of modes, it's how strongly you couple to those modes. So if you are going to the zero index limit, despite the fact that you are depleting the space of optical modes, depending on how your coupling strength evolves in that limit, you can have any possible limit. You can have that indeed spontaneous emission is inhibited, you can have that it could even diverge, or you can have that it converges to a finite value. And the same is expected for any other quantum transition and so on and so forth. So what it is interesting about near zero index media, as far as these quantum processes are involved, is that you can operate with a very low density of optical modes, spatial density, and that can allow you to have enhanced correlations maybe, but doesn't necessarily directly imply that you are inhibited all processes, again, because how strongly you are coupling to those modes is equally important. Okay, so for example, we evaluated this expression in the simplest case in which we have a homogeneous system for different numbers of dimensionalities, so that we can apply our results for one-dimensional systems, two-dimensional systems, three-dimensional systems, so that it is representative of waveguides and homogeneous media. And then you get a compact result like this. So basically, the pulsar enhancement is given by the median impedance multiplied to the number, to the refractive index to the power of the number of dimensions minus 1. Yes.
Sorry, like I'm totally confused. Maybe I'm missing something, but I thought that in if mu is equal to 1, and if you are in 3D, I was used to spontaneous emission being proportional to refractive index in the first power or square root of epsilon. So is it right? And you get refractive index to second power. I agree with all your arguments on the previous slide. Mm-hmm. Like you have two quantities, one is the delta function, another is the coupling. Yeah, I just wonder, the answer in literature always, I knew, was always n to first power in 3D.
Yeah, so let's double check. It's always dangerous to double check things live, but I think we can find a simple solution here. So when you look at this expression, so 3D will be d equal to 3, right? So you have the refractive index to the power of 2, right? But then when mu is equal 1, so in dielectric media, right? The normalized median impedance is 1 over the refractive index, so you get the result that.
Okay, thank you.
So we are okay.
Z depends on n. Okay, thank you very much.
Yeah. So for that particular case, but the thing is that even in the zero index limit, the spontaneous emission decay rate critically depends on the number of dimensions and the material parameters of the system. And even if your refractive index is going to 0, you can have non-trivial quantum transitions. So for example, here we have a few examples for 3-dimensional, 2-dimensional, and 1-dimensional system. For ENC media, mu near 0 media, and epsilon and mu near 0 media. So at the plasma frequency, we will have either the permittivity going to 0, the permeability going to 0, or the permittivity and the permeability going to 0. And we see that in 3-dimensional media, we get what the expectations could in general be. If we deplete the space of optical modes, spontaneous emission is inhibited. However, if you go to 1-dimensional media, you can have any result depending on the on the median impedance. So for 1-dimensional ENC media, you can actually have an enhancement of the spontaneous emission decay rate. For mu near 0 media, it is actually inhibited. So you have to be very careful about these conclusions. And this, for example, justify why ENC waveguides can have an enhancement of the spontaneous emission decay rate, despite the fact that you have a low density of modes. So it's a basic thing, but I think it is important to clarify it. Again, so why this happens is it's again because we have this expression for the Purcell enhancement, and we can write it as the product of two factors. How many modes we have there, which you could expect that the density of modes goes to the refractive index to the power of the number of dimensions. But when you have dispersion, is number of dimensions minus one, and then the group index, and then how strongly you couple to them, which is proportional, is basically dominated by the impedance and the group index. And it comes to the fact of how many energy per photon you have, or how strongly, for example, is your electric field per energy unit. And again, so that's the main message. It is as important as the density of modes as how strongly you are coupling to those modes. Okay. To finalize this, just let me say that I was using a super simple model where we have like infinite system and so on and so forth, but it is representative of some examples. So for example, if you have the usual epsilons near zero waveguide based on a metallic rectangular waveguide, the evolution of this of the decay rate fully matches those of the one-dimensional material with dispersive parameters. And sort of like the dual example, if you rotate the dipole and you change the PEC walls to PMC walls, you get the response of a mu near zero materials. So even this simple model is representative of some waveguides and physical systems. Okay, and there are many other examples. I'm going to cover another one in the next section. So again, so we clarify that, but there are more things to be careful about. For example, is that we are talking about decay rates at the near zero index point, but at the same time, we have that we are operated, the zero index point usually takes place at the edge of a bandgap, right? So we have to be very careful not to talk only about decay rate, but also talk about the non-perturbative decay dynamics that should kick in whenever you are operating near the edge of a bandgap. Okay.
May I just add very short comment? It's very nice. I've never seen this result. You also could consider an isotropic medium where, say, two components are 1 of epsilon and one is 0.1. So it is elliptic and one of the components is near zero. And actually, maybe several years ago, we have seen the same, that spontaneous emission rate also diverges if only one of three components goes to zero. So I guess it's aligned with what you now see in one dimension. So
yeah, it could be. It could be. We did not consider anisotropic systems. I wonder if there are, since you will be modes mixing there, I want to be careful.
Well, it's the same argument that you are given, absolutely. So you are depleting the space of the modes, but you are manipulating this coupling, and it diverges like 1 over this square root of the small permittivity. So it's similar to what you see in 1D, probably a little bit.
Yeah, it's probably the same. Like one set of modes in the anisotropic behaves as a one-dimensional system too. It is, yeah. It could be. It could very well be. Yeah, very nice connection. Yeah. I will. Did you publish that?
Yeah, I'll just send a link to chat. It's some PRB paper, nothing fancy.
Awesome. I would love to have a look at it. Okay. So okay, where was I? Yeah, so then we were discussing the decay rate, but you have to be careful to account for the full non-perturbative decay dynamics because you are operating near a very dispersive point. So we will reconsider the same problem with a more advanced sort of like formulation. The idea is very similar. We have a general simple model with a two-level system coupled to a bath of photonic modes. And then the idea is that the two-level system is initially excited and it decays to a superposition state where the excitation is either on the emitter or somewhere in that bath of photonic modes. If you solve the system instead of the weak coupling regime, if you solve it in a more general way, you can write the solution as an inverse Laplace transform, or it's equivalent if you do the resolvent operator method. So you can write it as an integral in the complex plane of a quantity which is the resolvent, which is basically defined by the self-energy of the emitter, which defines how the coupling to the bath of photonic modes is modifying the decay properties of your quantum emitter. Okay, and this will give you access to the non-perturbative decay dynamics. We are going to study it in yet another different implementation of near zero index media so that you can see several examples. This is an entirely circuital one, which may be useful maybe for superconducted circuit implementation or something like that. It is the usual metamaterial waveguide where you have this sort of like unit cell that will be repeated. And the propagation properties are actually equivalent to those of a equivalent one-dimensional medium, where you have both through the model for both the permittivity and the permeability, have different plasma frequencies. If you have different plasma frequencies, then you have a bandgap where you have a propagating band at higher frequencies. You have a propagating band at lower frequencies with a negative propagation constant, and you have a bandgap. On the edges of the bandgap, you have the ENC and mu near zero frequencies. So we can actually analyze both examples I was saying in the previous section. You can analyze them with this very simple waveguide implementation. So then again, we have to study the self-energy, which is dictating the decay dynamics of our system. And when you project it on the real axis, you get the decay rate and the frequency shift. And again, the particularities of this dispersive waveguide as compared to other waveguides is that you have an asymmetric band edges. So you have an edge where both edges are actually slow light, but again, because the coupling strength is as equally important as your density of modes and the group velocity that you have, in one of them you have an enhancement of the decay rate, and in the other one you have an inhibition of the decay rate and a bandgap. Okay. So now, again, if you want to have the full non-perturbative decay dynamics description of the system, you have to integrate the resolvent on top of the real axis. And by using complex analysis technique, you can transform it into the contributions from the different singularities in the complex plane. And since everything is characterized by this bandgap, you can see that you will have the usual suspects. So basically, you have unstable poles associated with the propagated bands. You have a real bound state associated with the bandgap, and you have contributions from the branch cuts, more complex. So basically, you have the usual suspects. The main difference with other dispersive waveguides is the fact that the band edges are asymmetric. Okay, and then you have to compute all of these contributions. For example, we can start with the position of the poles in the real plane. And for example, the projections of the pole positions in the real axis tells you more or less where are the spectral features that you will measure. And you can see that basically we have an evolution from unstable poles to bound state to another unstable pole. The difference again in the band edges, whenever you have a divergence, you have a splitted, and then the bound state continue to exist, while on the other edge, it looks smoother and you have like a softer transition from unstable pole to bound state, which may be interesting to switch from dissipative to coherent interaction. Then you have the projection of the poles on the real axis, and these are basically tells you how fast your pole is going to, the contribution for your pole is going to decay. And here we have that the decay rate is actually a very good approximation in most cases. And the main non-perturbative effect is a saturation of the decay rate for the edge with a divergence. So in general, you expect that you won't have a divergence decay rate because of losses and fabrication tolerances and so on and so forth. But the conclusion here is that even in the ideal system, you saturate the decay rate because non-perturbative dynamics are kicking. Okay. So then you have the contributions from the poles and you have the contributions from the branch cuts. The contributions from the branch cuts are tougher to analyze because you truly have to do the integral on the complex plane of both sides on the branch cut, and it's harder to draw like very simple conclusions or what are they. The main thing you can say is that they can be intuitively understood as a collection of contributions that lead to a fractional decay. So it's not like a single pole, it's a more complex contribution. If you write the expression, these are very difficult and tedious to write. But you can at least do the long-term limit, and you can demonstrate that in the long-term behavior, the contributions for the branch cut, they have a power law behavior. So again, you can at least intuitively understood that the branch cuts are giving you a fractional decay dynamics. So then the idea is that you combine all these elements in order to get the accurate description of the problem. And the weight or how this take will depend on the position of the transition frequency on your emitter with respect to the waveguide. So for example, when the transition frequency of your emitter is within a propagating band, the contribution is dominated by a unstable pole. When you are well in the middle of the bandgap, the decay dynamics are dominated by the bound state. However, when you are at the band edges, where you are near this interesting zero index point, you have all sorts of contributions coming from a superposition of the bound state, the unstable pole, the branch cut, and so on and so forth. And you have to take all of them again into account. So let me have a few examples. We have this self-energy, and we expect different decay dynamics as a function of the position of the transition frequency of your emitter near these points. So for example, if you are in a propagating band, basically you have simple exponential decay associated with an unstable pole. When you are in the other propagating band, maybe you have faster exponential decay because of Purcell enhancement, but still it really looks like exponential decay. When you are in the middle of the bandgap, the response is dominated. It's not entirely that thin, but it's dominated by the bound state. So you have this decay to a very long-lived state. However, when you go to the zero index point, you have a complex response. So for example, here, you will expect a soft transition from an unstable pole to a bound state, and that happens. And you will expect that at that point, there may be no decay, but actually there is fractional decay, even though it's small, there is fractional decay due to the contributions of the branch cut. And of course, the stronger non-perturbative effects are found near the divergence of the decay rate, where you have contributions again from the branch cut, the bound state, the unstable pole. So here we were expecting that you will have a very fast exponential decay. However, as you get to very strong coupling, what you get is a slow and oscillatory behavior due to the saturation of the decay rate, due to the non-perturbative behavior, due to the contributions of the bound state, and due to the contributions of the of the branch cut. So the idea is that you have to be very careful not to, when you are near the edge of this zero index media, not to only characterize the response of your system with the decay rate. You actually have wealthier responses in there. Okay. So finally, let's do some experiments. And this will be, I will be sharing with you the very first experiment that we have made in my group. So we are trying to apply some of these ideas to do thermal emitters and use ENC concept to do thermal emitters. The first one, we simply have used the fact that in zero index, in epsilon near zero media, the impedance gets very high in order to concentrate the absorption in a in a very thin, in an ultra thin metallic film. Okay. So then the idea, we want to concentrate absorption in thin metallic films, and the applications we have in mind are lightweight and dynamical thermal emitters, as well as thermal camouflage, because if you're able to concentrate the absorption in a metal film, you may have better tunability properties or maybe a higher dynamic range of change. It is also interesting for optoelectronic devices where you truly want to concentrate the absorption in the metallic film. And it is also great for photothermal modulation, because if you're able to concentrate the absorption in a very, very small quantity of material, you can have a higher performance of this photothermal modulation. So again, we are going to be using this property of ENC media, that it has a very high impedance. And this comes back to studies on microwave frequencies where they were using high impedance surfaces for antenna system. The idea is that when you have a high impedance system, you change from the PEC boundary condition to the PMC boundary condition. So you maximize the electric field on the boundary of your system, so you can have very strong absorption. And this is an idea that has been used for the design of electromagnetic absorbers, but it also has been used for the design of efficient low profile antennas, for example, here for satellite communications, for beam steering, and even for anti-radar systems. Most people and previous works use metamaterial structures or resonators in order to induce a high impedance surface. What we are going to do is to simply use the material properties of ENC media in order to get a high impedance surface that allows us to have efficient absorption on a thin metal film. And the advantages of this is that we don't need any complex nanofabrication process. It's a material-based approach that doesn't need any fabrication, basically. So then Also, because we are not using a metamaterial, we have no spatial dispersion and no restrictions of the geometry of the system due to the unit cell size. And this means that we can have operation in irregular and conformal substrates, right? Because the material is simply giving us the response that we want. Everything has disadvantages. So for example, in this case, the main disadvantage is that when we use a real material, we have material loss that limit the highest value of the impedance value that we can get. But still, the good news is that we have a relatively good high quality ENC medium, and we will be using silicon carbide because it has a permittivity which is has a near 0 point within the thermal atmospheric window. So it has synergies with technologies of thermal emitters, and it has a relatively actually very low value of 0.03 of permittivity with losses at that point. Okay, so we are going to the very simple system where we have a silicon carbide substrate and we will put a titanium film. So the idea is to keep the geometry as simple as possible so that we have efficient performance with no fabrication. That's the main goal of our study here. And then we can model this system very simply by using an equivalent circuit model, because we are also trying to absorb the energy in a film as thinner as possible. Okay, so then, since we have such a simple system, it is easy to optimize. Basically, we can only control the thickness of the metal film we are deposited, and you can derive what is the optimal thickness and what is the upper bound of the absorptivity you can get. So in theory, even with this simple system, if you have a refractive index going to exactly 0 and you will have a perfect resistive layer, you can have perfect absorption. And it has been demonstrated at microwave frequencies based on resistive layers on top of high impedance surfaces. However, when you have a realistic combination of a metal layer that has an intrinsic inductance and a real material acts as a zero index material, this will be the upper bound of the performance of absorption within the film that you can get. And again, this is absorption within the film, which is a much more difficult goal than absorption into the entire system. We want to concentrate the absorption into this nanometer film. So these are the calculations that you will get for a titanium film on top of a silicon carbide substrate. And basically, the spectrum that we expect of the absorptivity in the film will be something like this, where we have a peak of absorptivity at the ENC wavelength of silicon carbide and a minimum at the resonant frequency, simply following the dispersion of the permittivity, the plasma, and the resonant frequency. So basically, you have a system that doesn't have any particular geometry, but it has a very well-defined absorptivity spectrum just due to the material properties of the substrate. And as you can see, with a titanium layer, the maximum absorptivity that you can obtain in theory is limited, basically due to the properties of the titanium and silicon carbide. And in fact, if we were using a lossier layer, which will be a more resistive layer, you can actually get a better performance and a very high absorptivity, again, only within the film. Okay, so we fabricated these samples. Basically, we use e-beam evaporation on top of a silicon carbide substrate, and we did things of different thicknesses, and you can see how the entire thing becomes more opaque as we increase the thickness of the system. Some practicalities, we soon discover that using e-beam evaporation, the roughness of the system is going to play a crucial role, because you can have roughness comparable to the thickness of the film. However, in terms of absorption, this is not so bad, as we were saying, because a resisting film can actually have a higher absorptivity that very good metal that will have a higher inductance within the thin film. However, it may have detrimental impact on other impacts of the system. Okay, so these are the measurements that we did, reflectivity measurements via FTIR spectroscopy, and we get the results that we will be expecting. So basically, you have a highly reflective band corresponding to the points where your permittivity is negative. And then as you increase the thickness of the metal layer that we are placing on top of the substrate, then you get a reduction of the reflection. And we were able to correlate these measurements with the theory quite nicely. However, because of the roughness, we actually use the model of a lossy layer rather than the simple titanium response, which is okay, because actually, again, a resistive layer can give you a better absorption performance. Now, we were interested in concentrating the absorption in the thin metal layer, but it's actually tough to retrieve in practice. It could be done by doing like thermal emission, only heating the thin metal layer, but there is no port to measure how much power is absorbed in the metal layer. So the way we did to characterize it is actually to look at the reflectivity difference. This is only numerical simulations. The idea is the following: whenever you have a highly reflective band, if you put a lossy metal layer, reduction in the reflectivity is simply due to absorptivity within the film. This is an approximation that only works between the highly reflective band. However, it is a good approximation between the highly reflective band, and it is actually a conservative estimation near the ENC wavelength. So it is good for characterizing absorption near the ENC wavelength. And these are the results that we get. And as we can see, we were able to experimentally demonstrate that the absorption in the thin metal film is actually enhanced by the ENC response of the substrate without the need of any fabrication. And in fact, if you normalize this figure of merit, you can see that as you reduce the thickness of the system, you have a narrower response. So you can have a system in which the absorptivity on the metal film in the entire atmospheric window is dominated by this spectral feature on the ENC wavelength. And then the next experiment that we are trying to do is to apply this to irregular and conformal substrates. Because again, the advantage that we see on this technology is that you don't need any nanofabrication in order to enhance the absorptivity of the film. So you will get the same result even if you have different length scales for your system. So here you have a numerical simulation for sub-wavelength length scale to larger than the wavelength length scale. And we see that the absorptivity in the film will have the same spectral features with a maximum at the ENC wavelength and a minimum at the resonant frequency, quite independently of the geometry and the length scale of the geometry. So I wanted to share with you the very first experiment we have made in our group, and I hope we will keep pushing this forward. With this, I will actually like to finish my seminar. It's been like 1 hour, so very good timing. I would like to thank all the funding agencies that help us with make this research possible. Thank all the collaborators that have been contributing to all the work that I have presented. And if you're a student, the more important take-home message for you is that I have PhD and postdoc positions available at my group. So if you're interested to work either on theory or the experiments, we also have experimental works on integrated photonics. Just send me your CV to my email, and I will be delighted to consider your application. Thank you.
Thanks a lot, Iñigo. Very nice talk. So we have some time for questions. Colleagues, please raise your hands. And in the meantime, I would ask the first one. So maybe regarding the very first part of your talk, when you demonstrated that the distribution of Poynting vector in a 2D system corresponds to the flow of ideal fluid. So I wonder whether this conclusion can be generalized to 3-dimensional systems, let's say. What are the limitations here?
So we are working on that. I don't have the answer. The derivation that we did is restricted to 2-dimensional media. And it is restricted to 2-dimensional media because we use this very property that the magnetic field has to become constant. But this only happens for 2-dimensional media. In general, we have that the curl of the magnetic field has to be 0 if you have a near 0 permittivity. But it's only in 2-dimensional media that the curl can be written like the gradient dot product by the unit vector. And then you have this constant magnetic field that makes this operator goes to 0. So that's something I am working on. I do suspect that it can be generalized to 3-dimensional media if you have both permittivity and permeability going to 0. In the same way that for 2-dimensional system, you need permittivity be 0 for this polarization and permeability to be 0 for the other polarization. And in a 3D system, we have both polarization to be mixed, right? But that's something we are working on, and I suspect the derivation that we have published so far is restricted to 2-dimensional media.
Right, I see. And then another question related to optical forces, which you mentioned, which might be another interesting direction. So do you see some connection, let's say, between the force acting on this wing calculated in hydrodynamic theory from one side, and then this gradient force, which arises in the optical setup. So is there any connection?
Which force arises in the optical setup?
Yeah, gradient force due to the gradient of intensity.
That's a good point. So the gradient actually is more like a near field force. I never thought about it on a near on the gradient, because gradient force, I usually think like you have like a nano antenna or a metal tip, and that generates a strong gradient. This is more like a propagating wave hitting a large object, which becomes small. So I don't see a direct connection with the gradient force. What we see here maybe is that, for example, when you have airflow theory, you have that the drag force is 0 in fluid dynamics, and you have like a lift force, for example, right? So we are wondering if that will be the case. What we are trying to solve is, again, that we have a force of an object within a medium, so that has some particularities to evaluate. So that's what we are working on. How would you? Yeah, I don't see a direct connection with gradient force, but maybe if you have a suggestion how the gradient force plays a role here. Yeah.
Okay, thank you. So it looks very interesting. Some other questions from the audience.
I still have one regarding your very nice story about non-exponential decay of correlations for emitter coupled to a waveguide. So I wonder, have you already generalized it for, say, 2 emitters? So will you have some super radiance, sub-radiance, non-exponential sub-radiance if you have several emitters coupled to a waveguide?
Yeah, so we have done that actually. So this is something I put in preparation. It's going to appear in archive in 2-3 weeks. So please try to find it. We have worked on the 2 emitters case. The results are similar. Like we do have subradiance and superradiance. That will be the equivalent part to the unstable poles. So we have poles which are superradiant or are subradiant. And similarly, whenever you have a very sharp edge, you have non-perturbative effects kicking in that will make your response more complex. And then depending when you are operating, you are able to maintain a clean subradiance, superradiance or not. Yeah, but your intuition is totally right.
Okay.
So I do not see other questions. So I believe we asked a lot during the talk. Very nice presentation, Iñigo. Thanks a lot for joining us and giving a wonderful presentation.
Well, thank you for inviting me. This is truly a fantastic seminar, and I hope the series keeps on going. So yeah, this is ongoing. So we will continue until Christmas and maybe even later. Very good, very good. I encourage you to move forward even after Christmas. But yeah,
thanks a lot. Thanks. So bye everyone. Next time we have PhD attestation, 2 pre-defenses. One of them is Hadi Shamhi, another Stas Kolodny. So we're listening them in the usual pre-defense format. So stay with us. See you next time.